website of the assignment. You
All right.
have an example comparator, which
Oh,
is pretty
thank
much the
you.
exact same
I'm
thing.
going to save myself by having done this
I
before.
said that like 20 minutes ago.
You did it minutes ago, I'm sorry. Okay. Import Java Util Comparator. Class. My name comp implements comparator, my state. I have already done this for you, and it's already on the class page. Why are you making me do this? I'm sorry for wasting your time. Here we are. This is an example of a comparator. And I say so right here. Okay. If I use this, notice when I create my tree set, I pass to it a new my name comp. You see what I'm doing here? I'm making an instance of my comparator, which is going to compare them in this particular way. Okay. When you implement your priority queue, you can do the same thing, use a different comparator, and compare the other way. Okay, I've got to go eat some humble pie for this right now, and then I'll come back and answer some more questions. So, how are we doing? Do you get comparator?
So,
It's there on the assignment page. Basically, copy that. You're good. Okay. Let's take a step back and talk about, do you understand why we need to compare my states by cost, and why we need to compare them by x, y's, and why we're doing that differently in this assignment? Somebody say no.
no.
Why? What don't you get about that? Sorry. The reason we have to do that, the purpose of the priority queue is to represent the expanding frontier of our search, right? What represents that frontier? It's how much the path is costs. If the costs are the same, they're on the same edge of the frontier. Do you see why we need the priority queue to be sorted by cost? We need the priority queue to be sorted by cost so that we can always be expanding the frontier at a uniform rate. That's what uniform cost search is all about. Okay, when we ask the question, have we been here before, and we find somewhere we've been that has the same cost, does that mean we've been there before? No, in fact, all the places on this frontier have the same cost, or roughly the same cost. Some of them probably have exactly the same cost. Just because this node on the frontier exists doesn't mean we have never been to this node on the frontier before, right? So to ask, have you been here before, comparing costs doesn't cut it. We have to ask, have you been here before? And here is x and y. Do you understand why we need to compare by x and y? Okay, so they're totally different concepts, and they're both needed in order to implement this assignment. So you need two comparators. Okay, I think we can move on. All right. Now, why do we even need tree.find? Suppose you're here, and you can go here, or you can go here.
You
can't see. Oh, haha. Thank you. I'm over here on my laptop. I was having a private teaching session with myself. Let's suppose this costs 1, and this costs 3, and this costs 2, and this costs 4. We start our queue by visiting this node that I've highlighted here in red. We push that into our priority queue, and then we pop something out of the priority queue. What comes out? That red node. And then we ask it the question, okay, give me all of your neighbors. Well, it gives us this one, and it gives us this one, and we push them into the priority queue. Well, the one on the left has a cost of 1. The one on the right has a cost of 3. Which one's going to come out of the priority queue first? The 1. So the 1 comes out of the priority queue, and we say, okay, give me all of your neighbors. Well, there's only one right now. Maybe there's another one down here. But the point is, the cost to get to this white node that I have, there's two white nodes. This yellow node, the cost to get to the yellow node is clearly 5, right? At this moment, we create the yellow node and we give it a cost of 5 because that's the way it is. What is the true cost of going from the red node to the yellow node? Oh, dang. Okay. At this moment, we understand the cost of going from the red node to the yellow node to be 28. But the real cost of going from the red node to the yellow node is 5. So we don't actually have the right answer until we pop another node from our priority queue. When we do, this one comes out, this other green node. And we find all of its neighbors, and we find that there's a path that goes here to 2. And so now the cost of going to the yellow node used to be 28, and now it becomes 5. Do you see how there's a problem here? This is the problem that came up with breadth first search. Just because you found it first does not mean it's optimal with uniform cost search. Because this situation might actually happen. Can this happen in this assignment? Well, imagine that you just had 4 pixels lined up, just like this. Isn't this the same situation? You're right here, and the cost of going this way might be that, and the cost of going this way might be that, the cost of this way and the cost of that way might be something like that. That's pretty much the same graph, right? There is one mitigating factor. The cost is always the cost of the pixel to which you're transitioning. And so as it happens, this one will never be a totally different value than that one in this assignment. So it turns out if you don't bother going back and updating your connections, it will work in this assignment. Let me describe that in terms of code. If you're right here in the pseudocode and you simply omit this if statement right here, if child is in bin there, then get it and update its cost, it'll still work in this assignment. That's unfortunate because there are cases where that doesn't work with some grids or graphs or different rules of problems. So if you just want to pass off this assignment, you can forget about this and not even worry about that whole thing about set not having a find method, and you'll be okay. However, if you want the correct implementation of uniform cost search, you need to be able to back patch the costs like that because this very situation, not that one, this one might occur. Okay?
Wouldn't that
Follow
change the path?
It does change the path. So yeah, let's look at this code. Right here, if child is in bin there, meaning what has actually happened is we've already found this path that goes this way and it has a cost of 28 to get there. And now we're coming along this way and we go there and we say, oh wait, we've been there before. So we're saying, have I been here before? And if you have, which occurs right here, if child isn't bin there, the old child equals bin there dot find child, meaning we're going to go find the one in our set that we've seen before and see what its cost is. And if its cost is wrong, if its cost is higher than the cost that it's going to get, then update its cost with the new cost. This is the cheaper cost. So we're essentially saying, yeah, we know we found this cost of 28 to get there, but now we found a cost of 5 to get there. 5 is less than 28, so this becomes the new path. And we're going to, its parent used to be this one. We're going to switch it over to this one because that's the new best way to go there. Okay. So that particular clause of the pseudocode right here is handling that case, the one case that doesn't actually occur in assignment 2. Okay. aside from that, tell me, have you looked through this pseudocode and does it make sense to you? Okay, the main thing I really want you to get is, look, there's a frontier. We seeded the frontier, and we're just going to pop it out and push all the neighbors back in. Repeat, 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 until we're all done. This one case is what we have to do for the cases where we find new paths that are actually better. That's all there is to uniform cost search. There you go. Yeah.
Will we need the bin there for assignment 3?
Thinking about it? Maybe? No, you won't. Dang it, I have got to update these assignments so you need that. I haven't done it yet, so yeah, if you want to omit from right there to there, you're okay. Although, why would you do that? It's only that much code, and you want your code to be awesome because you're going to use it again someday. You know you will. No, you won't. But you should. You really should write good code. Okay. All right.
I thought we used bin there in assignment 3 because you didn't want to look at the save board twice.
Yes, you will use a bin there in assignment 3.
So we don't have to update the cost.
But you won't have to update the cost. Here's why. In assignment 3, the cost, every action has a cost of 1. And because, imagine if you were to do this situation and all of these states were 1, 1, 1. Well, if you find a path to get there, it's going to cost 2. So if you find another way, well, if it's less than, you would have found it first. So that doesn't occur with breadth first search. Okay? So in assignment 3, you're actually using breadth first search rather than uniform cost search, so there's no way this problem could come up. It just doesn't happen to come up in this assignment because of the way we measured the cost of the transitions. Okay. My feeling at the moment is this. I don't think anyone has trouble with the algorithm. I think a lot of you are going to really struggle with Java. Is that fair?
Yes.
Yes.
Okay, thank you for admitting it. I need to talk you through Java a little bit. Okay. Here's a Java example of a tree set. Use this example. Here's how to do a comparator. This is the right way to set up both your priority queue and your bin there sets. There's that. Do you have to use a tree set? What's a better structure you could use? Hash map would be a really great data structure to use. Why is a hash map better than a tree set? Yeah, it's faster. Basically, tree set is going to use log n time, hash map's going to be order 1 time. The difference is you have to write a hash code function, and that can be confusing too if you don't know what you're doing. So if you just don't get hash sets, I gave you an example of a tree set, just use it. It'll be fast enough. If you do, though, they're probably as easy as tree sets. Is that a good assessment?
If you don't want to write a hash function, Java object has a get hash.
That is true, but the get hash doesn't by default rely only on the things you want. So when you're sorting your, let's see, in your bin there, you want to say, yes, I've been there, if you have the x and the y right, but even if the cost is different.
Oh, right.
The built-in hash code doesn't necessarily know hash the x, hash the y, don't hash the cost. And so if you do that wrong, you'll end up getting wrong answers, which will throw you off and confuse you. So you do need to be careful about what you're hashing. Yes?
You could avoid that by just keying it with a string being x comma y.
Yeah, you can. But you'd have to know to do that, is kind of what I'm saying. If you know to do that, use hash map. It's great data structure. Or how about listen to this? You need to do that. Okay. All right. Another issue that I know I'm going to face, and I'll just tell you now so I won't have to face it, is the deep copy issue. Make sure you're not putting the same MyState instance into your queue over and over and over and updating its x and y position, right? Do you know what will happen if you do that?
Frontier will continuously expand.
Well, in fact, you'll have the same object put into your frontier over and over and over, and you'll keep changing what's in that object. So even though when you put it in, it had these values, when it comes back out, it will have completely different values. That would just really mess up the algorithm, right? How do you make sure you don't do that? Yeah, basically every time you have a neighbor and you're going to push it into your queue, make sure you're allocating a new MyState and putting a new MyState into your queue. That way all the MyStates in there are unique. And as long as they're all unique, you're not going to be messing up ones that are supposed to have different meanings. Okay. If you didn't have me in paradigms, you might struggle with this. If you did and you struggle with this, I boot you in the pants. Okay. There's that. I don't know what else to say about Java. Is there anything else helpful that someone can bring up? I think we're ready for this assignment. I'm just going to say it's due tonight. Well, I already did. It is due tonight. I will try to monitor the forum, but I'm busy, so I might not. But you all can answer on the forum too, so let's help each other out and let's all do the assignment together. Wouldn't that be grand? We could all help each other out. It'll be super easy, super fun. Any other questions you want me to answer about it? Thank you.
In the instructions, it asks for a build script named build.bash or build.sh, but the grader asks, or it looks for build and run.sh. Does that matter?
That doesn't matter at all. My build script will look for build.bash or build and run or build.sh. It tries a few variations. It shouldn't matter which it is. If it ends up being some dumb issue like that, just send me an email and I'll work with you. Let's see. This says it looks for a file named build.bash.
Build.bat works too.
Build.bat works too, because I've had plenty of Windows users work with me over the years. Basically, just don't do something weird and name it hi.yo, because then it won't find it. But just call it one of those names that makes sense for a build script, and I've probably thought of that before, and it will find it. It's a good idea to unzip your own archive and run the build script before you submit. That'll tell you what it's actually going to do on the server. It'll do the same thing. When you submit, it should execute and build, and you should see the output. So you should find out exactly if it worked right then. And if it didn't, fix it and submit again. It's okay to submit as many times as you want. Okay. How much time do I got? Any other questions? Started putting my lectures online again. You notice the lectures got a lot nicer? Everybody see it? That's because we're recording them over here, in case you didn't know. This is not the video to which I referred last time, but it's almost the same concept. I figure they must have probably got sued by, name's escaping me now. Kasparov, who they were parodying before, and so they made a different one. That's my best guess. I don't know. But same vein. If we look down the schedule, I added 3 of these, faculty candidate presentations. What's happening is we're trying to hire some more faculty members, and that means we're going to fly 3 people out here, and they're going to give presentations. I would encourage you all to attend their presentations if you can. Basically, these people have probably recently finished a PhD, or else they've been teaching elsewhere, and that means they're world-renowned experts on something. And it might be something weird, might be something you don't care about, but they've spent a lot of time studying something and presumably have something good to say, so it might be worth your time to attend those. Another good reason is If any of you are interested in graduate school, one of those people is going to be our another faculty member here. So you might want to become familiar with their area of study, and that's another good reason to attend their presentation. If you're not going to be a graduate student, hey, you can still show up and evaluate them and help influence the school for the better. So if you're not doing anything at this time, it would be really cool to sit through their talk and give feedback about them. So you all have formally been invited to attend those things, and I stuck them on the calendar for you. So let's ask a question. You're working on assignment 2 now. You're coding along. You think you did it all perfectly. You followed my pseudocode, and the thing doesn't work. What do you do? You stare at your code until your eyeballs bleed. You get frustrated. You get angry, right? No, that is the answer right there. Usually you've been taught to chop your code in half and figure out, did the bug occur before or after this point? And did the bug occur before or after this point? And you use binary search to find your bugs, right? This is, however, it's not that much code, and you've got a loop, and it's doing it over and over and over and over. Is that going to work? Maybe. If you're a good debugger, it probably will. But it's going to be kind of hard because you're doing the same thing over and over and over and iteratively converging towards the answer. So if it's doing something weird, it can be really hard to wrap your head around what's going on inside of these loops. For that reason, if you cannot simplify the code, simplify the problem, right? Isn't that how you debug it? So if I had code and it was all written and I had no idea where the bug was, here's what I would do. I would open up my favorite painting program. I'd go to resize and I'd change it to, let's go a 2 by 2 pixel image. Now that is a darn tiny image. And let's just give it some, hey, that's a 1 by 1.
You should have used the pencil instead of the paintbrush.
Oh, it wasn't. It was a 2 by 2. I had a paintbrush. There. Now I have made an image, and I'll save it. And I'll have to tweak my code so my starting point is 0, 0, and my goal is 1, 1. But now you can step through this, right? And that's going to be totally comprehensible. You can get out a piece of paper. You can write down where you've been. It's going to max out at 4, so this is not going to waste too much of your time. You can track everything that's going on, every cost, every step, and you can see where it messes up or where it gets it right. Now, what do you do if it gets it right? Make it bigger. Make it bigger, yeah. Not much bigger, though, because you don't want to. Go 3 by 3. There. And the point is, you want to find the smallest, simplest case where your code fails, and you want to see it fail, and you're going to step very carefully through your code, just tracking everything that's going on. Then you found your bug. Once it works, try it on the big problem, see if you get the right answer. If you do, yay, turn it in, you're done. Okay? That's how you debug code that you can't possibly debug. You debug the problem. Okay. Let's see, that. Okay, next topic. Switch back. I want to talk now about what kinds of problems uniform cost search can solve. What kinds of problems can uniform cost search solve? So let's suppose the start is here, the goal is here, and it's a really, really complex maze. And let's suppose this maze is so difficult that all humans who have ever attempted it have said, this maze is too difficult and have given up. Can uniform cost search solve that problem? Yeah, in fact, this is pretty much the ideal problem for which uniform cost search is well suited. It will find the way through the maze. It will find the optimal path through the maze. This is basically a maze runner that you're coding up. And it's as good a one as exists. So this is the problem for which this algorithm was designed. What if the goal is to get from start to the goal, but there's a wall around it such that there's no solution? Well, it will find that there's no solution. So I guess you can call that an answer, right? So as it searches outward, it'll eventually hit the wall. Pretty soon it'll run out of places it hasn't been. Once it's been everywhere, that tells you there is no solution. It will determine that, so I guess that's as good as you can do. Can it solve it? Well, no, there's no solution. What if there are multiple goals?
It'll find the shortest path to the closest goal.
What does it do? Yeah, well, it depends what you mean. What, by multiple goals, is your goal to find all three goals, or is your goal to find the first goal or the shortest goal, or what do you mean? Let's suppose your objective is to find whatever goal is closest to you. Yeah, it'll expand its frontier until the frontier reaches a goal, and as soon as it finds a goal, you found it, it's done. What if you wanted to find the shortest path to all three goals? How could you use uniform cost search to solve this problem? You could run it 3 times and each time pick off a goal. Yeah. That's one way to do it. I think you can be slightly more efficient. Why not just keep running? Like count how many goals you get, and as soon as your counter gets up to 3, then be done? Because there's no reason to repeat searching outward from here. You might as well just keep going, right?
The quickest path might not be necessarily going to the shortest one first, right?
That's true. Well, so I guess what would happen is suppose so you've got this path that gets to goal number 1, and you've got that path that gets to goal number 2. This would be one node, and this node, each node would have these pointers to their parents that get you back to the start, right? So by the time you've found all 3 goals, I think you've found 3 completely separate paths. It's just they happen to go through whichever node finally found each of the goals. Its parent and its parent and its parent and so forth will represent the path all the way back to the start. Then you can reverse it to get the path to each of the goals. So essentially, just by continuing until you found the last goal, you can solve that problem. Okay, what if you don't know how many goals there are? And your objective is to find all possible goals. Can uniform cost search solve that problem?
For a finite map, yes.
Yeah, as long as you have a finite map. Suppose your map has an infinite size, how do you know? Well, it's the halting problem, right? It's the, how do you know when to stop? You don't, so it can't. Okay, now, what do you do if okay, here's another question. What if there are wormholes in the game such that if you enter into here, you come out right here? And let's suppose that there's a whole bunch of wormholes scattered all over this game. So you can go in here and teleport over there and go in there and teleport over here. And now I'm going to use uniform cost search. Just to keep it simple, let's go back to the one goal situation. Now I'm going to use uniform cost search. Will it find the optimal solution to the goal? Who says yes? Who says no? Nobody says no. Well, good, because the answer is yes. Essentially, this doesn't really change the problem at all. Do you see why it doesn't change the problem? It changes the problem for you as humans because you're used to spatial reasoning, but it doesn't change the problem for the permutations that you could possibly perform that get you to the goal. The fact that you can go in here and come out here is really